Hello.
Hello.
Can you see the desktop?
Yep.
Okay. Let me get set up. Okay. All right. So I forgot to. I don't have an entry for today yet. I didn't get a chance to update the website for today. I'm going to show you some code that I wrote that I'm trying to do something simple, trying to parallelize something simple, and it's actually turning out to be. It's interesting to see how hard it is to write code, what it boils down to. Okay, so let me show you what I've got. Okay. Okay, here's the folder that has a huge text file in it. Okay, so I'm actually working with, see, actually, I can make this a lot easier. I'm actually only working with all these files for now combined into this one file. So let me do something here. Make life a little bit simpler by copying all this to a new folder. Okay, instead of having 1,000 files in the folder, okay, our job is to, this is a 2 GB text file, actually a little bit over 2 GB. It's a about 2¼ GB text file, and I want to search it for the word aardvark. Okay, that's the goal, is to search this file for the word aardvark. To give you a benchmark of what we would like to do, open the file with TextPad. TextPad can open the file in about 20 seconds. Okay, so TextPad opens the file in about 20 seconds. If you call up Task Manager, you see that was TextPad allocating memory for the file that it just opened, about 2 GB of memory. Okay, now TextPad, go here and ask it to search for aardvark. Okay, okay, and have it find all. Takes TextPad about, it took about 20 seconds to open the file, and it takes about 20 or 30 seconds to search the whole file. So TextPad can open the file and search it. There, see, it's done searching. Whoop, oh, darn it, I clicked the wrong button. So now I'm searching again. But it opened the file in about 20 seconds, and it searches the whole file in about another 20 or so seconds. Okay, click close, and then here's all the aardvarks in the file. There should be about 20 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 27. But this time I searched for aardvark both uppercase and lowercase. The aardvark we're going to do is searching for only the lowercase. So if I do that again, I can click here on match case. Okay, so but there's a benchmark. Okay, a program can open a 2.3 GB file and search it in well under a minute. Okay. Okay, so we know now that it can be done in well under a minute. Okay, so now let me show you some examples of what I can do. Okay, start with a sequential search of aardvarks. Okay, So here's a sequential search that it's not going to try to be parallel, okay? And it's going to be pretty close to what you would think would be the right way in Java to search, okay? So you have to create a file input stream. We turned it into a buffered input stream because file input streams aren't buffered, so that's not a good way to process data. We saw the other day that buffering matters, so we make it into a buffered input stream. Then create a scanner around the buffered input stream to make it easier to work with, okay? Then read lines from the file. Every time you read a line, you increase this line number, okay? Then take the line, trim it, split it on punctuation, so that gives you words. Then for each word in the tokens, the split line, if the word equals aardvark, print out a timestamp and the line number, okay? Real straightforward. It's just a few lines of code. Basically, you open the file, read it line by line. Each line gets scanned in, split, and then you search the line for something that equals aardvark. So it looks like a nice way to write the code. Turns out to be absurdly slow, okay? So if you compile this and run it, it's going to take about 4 minutes to read that file, okay? I'll let it run in the background. See, it found a couple aardvarks already, okay? See, it timestamps each aardvark and gives you the line number of where it found it. And you can verify those line numbers with TextPad, and they're the right line numbers, okay? All right, and it's going to take about 4 minutes, okay? Which is not good because we know that TextPad can do it in under a minute, okay? Now, here's another version of the here's another program, okay? Now this one reads the file through standard in. It doesn't open the file. It just assumes that you're going to read the file through standard in. And it does things at a very low level, okay? And I'm going to let the other one run for a little while. Oh, actually, you can take my word for it. It takes 4 minutes for it to run because I don't want to waste time. You can check it yourself. You'll see that it takes about 4 minutes for it to run. Okay. Now here's another here's another way to search that same file. I'll compile this, and then when I run it, I'll give it the big data file as standard in. So I'm going to run this program with the big data file as its standard input. That took 5 seconds. Okay. We've now got something way faster than TextPad. That actually did it in about 5 seconds. If you want, we can, now notice I've gone from 5 minutes to 5 seconds, okay? Open a command window and run it from the command window so you can time it. That was, this one, I think. Okay, 5 seconds. That's pretty impressive. That's still serial program. That beat the pants off of TextPad. It opened the file, read it, and searched. And again, you can double check with TextPad. Those are the right line number. Actually, they're not quite the right line numbers. Some of them are off by 1. It seems that there's the data file's messy. And so I think somewhere in this data file, there's a stray /n that's somehow throwing off the line number counts. So starting at about the middle here, the line numbers are actually off by 1 compared to what they should be, okay? But there's 21 aardvarks in there, okay? And it took just a hair over 5 seconds to open that 2 GB file and search for all the aardvarks, okay? Now, look at the difference in the kind of code that, here was the high level way of doing things where you open the file with a buffered input stream and you use a scanner and you scan a line and tokenize it. Okay, that turns out all this library code is slowing things down a lot, okay? Here's a very low-level program. It creates its own buffer, okay? Then it's going to use system.in with a low-level read function. The low-level read function just reads into a buffer. It doesn't read lines or anything like that. It just reads into a buffer. So now I've got an array of chars, and I need to search for the word aardvark in it. So I'm going to walk through the array, byte by byte. I'm going to walk through the array, byte by byte. If I find a /n, I've found a line ending. So I increment my line counter. If I didn't find a /n, I look to see if well, I don't want to get to the end of the array because I can't find the word aardvark if I'm at the end. You know, if I'm less than 8 characters away from the end of the array, I'm not going to find the word aardvark. So I check to see that I'm not at the end of the array. Then I just look for AARDVARK in in 8 sequential bytes. So I'm using Java's short circuiting here. You might think that this was slow because I'm writing a big crazy if statement. But it turns out this is like 50 times faster than calling equals. It's way faster than saying s.equals aardvark. Okay.
Why wouldn't the equals just compile down to what you had in the other file?
I'm the wrong person to ask that question of. You're supposed to ask the guy who wrote the you wonder why it's, I don't know. I don't have a good question. Why wouldn't it just be doing something as super as now? I might be wrong. It might not be the equals that's slowing this down. It might even be this split, for example. Maybe it's the split that's really slowing it down.
I know that in R, that same function split is damn fast.
Well, you'd expect it to be optimized like crazy because split is used a lot. Splitting
It's really useful.
Yes, it's tremendously useful because this kind of code is this is not fun to write.
No, it's not.
And it's real easy to be like, for example, first of all, this is wrong. This does not give you the right answer.
Wait,
I
what?
dare you to figure out what's wrong with this. It's flat out
God.
wrong.
Oh,
This is right. This will always find the right answer. This will undercount the number of aardvarks. Think a little bit. I read in an array of strings, an array of characters. I read one buffer full, then I search that buffer for aardvarks. Then I read in another buffer full of characters and search that buffer for aardvarks.
Almost certainly gonna miss something either at the last buffer full or the first one.
No, not the last and the first. No, it could be anywhere. But what am I going to miss? I'm going to miss aardvarks this way. Now, the probability of missing an aardvark is very low, but I definitely could miss aardvarks this way.
It like I'm saddling between two
Yes.
buffers.
Right. When an aardvark straddles two of those buffers, I'm not going to find it.
Those are big buffers, so yeah, you're unlikely to miss something.
Yeah, I'm using a fairly big buffer, so the odds of that happening are not great. But this is wrong. This is flat out wrong. That's why you don't want to be rolling your own code, low-level code like this. I really need to check that what if I found those letters at the end of one buffer and found those letters at the beginning of the next buffer? Oh, that's a pain to write.
What you could do is you could have two buffers kept in memory. So
there's a lot of things I could do. I know that. But the trouble is, I'm pointing out that there's a reason why people write high-level code.
It's easier and it's guaranteed to work.
Right. And it's also, if you're not lucky, guaranteed to be really slow. We went from 5 minutes to 5 seconds. Okay. And now, if I did this right, it will be just as fast as it is now. But I could make this correct, and it'd still be fast. But I'd have to start writing very touchy code that could be easily off by one. But the trouble is, notice how hard it is to write fast code. It's
I see a lot of opportunity in there for one-off errors.
yes. Oh yeah, me. Oh yeah, I know there. I've seen them already. Yes, there's a lot of opportunity for one-off errors, but at the same time, you're getting the speed you want. Okay.
Mhm.
Now, okay. So this is guaranteed to be correct because it's doing things by line, and then it's only searching within a line. And you know, the word aardvark can't straddle two lines because by definition, the word aardvark has to be one word on a line. But this guy doesn't straddle. This guy's not line oriented. It's buffer oriented. It's too low level, but it's blazingly fast. And this is one of the paradoxes of trying to write fast code. Lower level code's going to be fast but hard to write. Higher level code is going to be easier to write. And unless the library people have really worked hard for you, and this is their goal, is to make it easy for you to write the code, but they can still guarantee performance. I'm not getting it here. Now, I don't know if the problem is equals, or if it's split, or if it's the scanner. I actually don't know where the bottleneck is. Profiling might, I haven't had time to do this, but profiling might let me know whether it's the scanner that's really the slow thing, or if it's the split that's the slow thing, or if
From
it's
what
the equals, or if it's all of them.
from what I've read, it ought to be scanner, because the way that scanner works, from what I hear, is that it doesn't buffer anything. Every
I've already
call.
buffered it. I buffered it over
Oh, you
here.
did buffer it.
Yeah, see, I supposedly took care of that. Yeah, yeah, I buffered it before wrapping the scanner around it.
All right, never mind. You
Yeah,
already knew about that, so
but it
that it
still doesn't mean that
shouldn't be scanner.
it might still be the scanner that's the slow thing. I just don't know. I mean, yeah, okay. So now I've got something that's really fast. I mean, now here's what's interesting. Would it be worth my while to parallelize this program? Not really,
Probably
because
not.
you know, I, who knows where the bottleneck is? If I parallelize something that I know is slow, then I don't really know if I'm gaining anything when I parallelize it. And this is a big problem when writing parallel code. You've got to start with something that you know is reasonable. Otherwise, you may just be parallelizing a bottleneck and getting a lot of parallel bottlenecks. Okay, so I'll probably want to parallelize this thing. Okay, now this thing's already under, okay, this thing's at 5 seconds. I've got 10 cores. Oh, maybe I can get this thing down to half a second. Maybe I can parallelize this thing down to half a second. We'll see. Okay, so I've got easy to write, correct serial version that's slow, a kind of flaky, very fast, low level serial version. Okay, now let's play around with trying to parallelize it. Okay, let's look at parallelizing it. Now, first I did parallelize this one. I took this one here and I parallelized it. Using thread pools, okay? And what it does is it splits this work here into 2 steps. One step does the I/O. We talked about this the other day. I'm going to split it into 2 steps. A step that does the I/O, then a step that does the splitting and the equals, okay? So I split this thing into 2 pieces. Well, actually, in this one, I don't really need to split it into 2 pieces. I'm going to, the way this one's going to work is the main method is going to do the I/O. So I'm going to have the I/O is going to be done in the main thread, and then the splitting and equal is going to be done in the thread pool. Okay, so remember we were doing those programs that had multiple streams input. Oh, they're not in this folder. We were doing folders that had multiple streams. This folder's only got 1 stream. So I only, I can't parallelize the I/O because there's only 1 stream. Okay, so there's no potential for parallelizing the I/O in this case because there's only, I'm opening 1 big file. When I open lots of little files, then there's the potential to parallelize the I/O part. But here I can't parallelize the I/O part. Okay, so the main thread, his job is to read one line, and when he's got a line, stick it in the pool for a worker thread to search for the word aardvark. So the job of the main thread is essentially to split the file into lines, and for each line, throw a task in the thread pool. Okay, and then have worker threads pull lines out of the thread pool and do this part here. Okay, say they split the line and then search for the word aardvark. Okay, all right. So one thread does all the I/O as fast. Essentially, notice that once it's read a line, it's trying to do the I/O as quickly as possible, because once it reads a line, it basically does nothing but with the line but stick it into the thread pool. Then it can read the next line. So it's going to read lines as almost as fast as possible through that file, because once it's read a line, it doesn't do much of anything with it other than build a new task and submit it to the thread pool. I doubt very much if submitting something to the thread pool takes very long, because the whole point of thread pools would be to have this submission to the thread pool be super fast. So I don't think this could be a bottleneck. I don't think it could be. Okay, so the main thread is reading lines as quickly as possible. For each line, it just builds a task, throws it in the thread pool, then lets the thread pool, then the work builds up in the thread pool, but then the thread pool is going to have as many threads as I have cores. See, I gave the thread pool 12 threads. So the thread pool can be pulling work out of the thread pool as fast as possible and keeping all the cores busy. Okay, so now this is parallelizing something that we know is really kind of slow to begin with, but we can speed up a slow thing and get something that's a faster slow. Okay, let's see what happens if we run this. So compile it and then run it. If I remember right, this definitely speeds up. The parallelizing thing speeds up, but it's not impressive. It may go from like 4 minutes to 3 minutes. Even though you're running it now, look at my cores are busy as can be. I think it's the split is really, my cores are working like crazy now. There's 12 of them flailing away at this data, but notice that aardvarks aren't showing up over here. It actually is only, it's not much faster than the serial version.
It looks like you might be memory bottlenecked. You're.
Oh,
I'm a,
no,
look at.
no, I'm not,
No, I mean, I'm memory speed, like memory bandwidth, because look at how your CPU usage is distributed.
Pretty weird.
Hyperthreading occurs when you have one core waiting on data from your main memory.
Half the cores are pegged and half the cores are only at half usage. So
that means that you have half your cores just not being fed with data. I'm presuming those are the extra threads on each core. So you might just be hitting cache all the time.
I don't really know what to make of it. Profiling it might help figure out what's going on, but we're taking a program that was slow to begin with and parallelizing it, and the real result is it's not very useful. I mean, it's not much value to parallelize code that you actually know isn't really that performant. Okay, and this is a lesson a lot of the textbooks don't really point out, because like I see it a lot. They parallelize code that really isn't very good to begin with, and it does run on lots of cores. I can congratulate myself that I managed to use all 12 of my cores, and I've used them all to accomplish nothing. And actually, I see it when I look at what's in textbooks. It's really discouraging how much this is what's going on. It's let's write parallel code. We'll peg all your cores, and we won't write anything that's faster than what we started with. But we will use all your cores. So that's exactly what I've got here. I've gotten a good textbook example of parallel code that accomplishes nothing. Okay. Now, if we take the better code, we'll see some gain. Okay, we will see some gain when we parallelize the code that is not bad. So this thing, notice, I've been talking for a while. This thing's already been running for about 2 minutes. Yeah, I think it's gonna go from, like, I think 4 minutes to 3 minutes. Okay, so we know by now that this didn't do any good. With 12 cores, we should have been able to parallelize something that took 4 minutes to be well under a minute with 12 cores. Okay, all right. So now you can see all the thread pools all shut down now. Okay, now let's look at another. Now let's parallelize the one that's kind of the low-level one. Let's go and parallelize this low-level one. Same idea. We're going to split this into 2 steps. One step that finds the line endings and builds a line, and then another step that does the computational search. Okay, now the code gets even messier now. Where is it? Okay, it's this one here. Okay. Well, okay, let me run this. Notice it's not get. See there. Took 2 seconds. What is that? 20 seconds. Not bad. 20 seconds. Okay. Okay. The serial one was okay. But the serial one was 5 seconds. Okay. The serial one was 5 seconds. We've parallelized it, and we've managed to slow it down by a factor of 10. But we did use all our cores. Okay. This is how crazy parallel programming is. Okay. I took a serial program that ran in 5 seconds, ran it on all of my cores. You can see it was running on all my cores. It's almost gone, but you can see it was running on all my cores, and it's way faster than the other version that was parallel, but it went from 5 seconds, let's see, to 20 seconds. Okay, went from 5 seconds to 20 seconds, and it used a whole bunch of cores to do that.
You might be better off trying to split the file into multiple segments, one per core.
Well, okay, but
or per thread of execution.
Well, we've got it split into 1,000 files. And at some point we'll go look at trying to process the data in 1,000 files. But the goal, see, the idea here is just set a problem and see what's the best way you can solve that problem. I mean, right now the problem is I've got this one big data file, and the question is, what's the fastest you can process that data file? Now I know I can process it in 5 seconds. I've got it here processed in 5 seconds. Okay. So if I can do it 5 seconds with 1 core, why can't I do it in a half a second with 12 cores? Question is, how do I parallelize it? I know I can do it in 5 seconds with 1 core. Now let's look at how this was parallelized and see, like, where it might not be, where it might be improved. What could be slowing this thing down? Okay, this is very close to being here's the sequential one that's super fast. No, that's not the sequential one. The sequential one that's super fast is, here's the sequential one that's super fast. Okay, remember, it read into a buffer, found line endings in the buffer, and those were line, it did a line count, and then it just walked through each buffer looking for aardvarks And as long as the aardvark word didn't straddle two buffers, it would find the aardvarks. Okay, but we know that it's buggy. It won't find aardvarks that straddle two buffers. Okay, what I'm doing here now is same buffer. I'm reading from the file input stream. Okay. Oh, this one did read from standard input. I don't know if that could be one reason why this was faster. This one was reading from system.in. This one is opening the file with a file input stream and then reading buffers full directly from the file input stream, as opposed to reading buffer fulls from system.in. I have no idea if that's possibly, maybe I should switch this one to using system.in. We can actually switch it real quick in a minute, see if that speeds it up. But this one was actually opening the file, not using standard in. Until you experiment, you don't know what could be the problem. So there's a potential difference. That could be where the slowdown comes from. Okay, then what does it do? The main thread walks each buffer, looking for line endings, and when it finds a line ending, it builds a string out of that part of the, it builds a string in between two new lines, okay? So what it's doing is every time it finds a new line, it builds a string object between the two new lines. So I build a string out of the buffer. So I have to build a string. Now, here's another problem. In order to pass information from this worker to the thread pool, I need to put the work in a string. Building that string might be my performance problem. You know, maybe my performance problem is building the string. This guy, because he was single-threaded, he didn't need to pass information from one place to another. Now, this is a good point. When you parallelize things, a lot of times you have to pass information between the parallel parts. And sometimes the passing of the information is what slows you down. You know, the passing of the information between workers can be the bottleneck. So that's one possibility here, that the bottleneck is that I have to pass a string from one thread to a worker thread, and building that string may be my bottleneck. Okay, so there's another potential bottleneck, building that string. Now, once I built that string, I pass it on to the worker thread. The worker thread is just like this loop here. The worker thread pretty much, well, not quite again. See, the worker thread is walking through an array. This worker thread is walking through a string. So instead of doing probably what are much faster array access, this guy is going char at, char at, char at, char at. That's another potential slowdown. Okay, I've got a string and I don't call equals, but I do have to step through the string one byte at a time, calling char at. Well, now you would think that this char at would be optimized to be an array access, right? Because a string is nothing but an array of bytes, and this is an array of bytes. Okay, but maybe not. You know, so notice I have a bunch of question marks here. Is using a file input stream slower than using system.in? We'll check that in a second.
Do you know if chars are a byte or 2 bytes?
In Java, they're not bytes. Well, it depends on the character set that you're working with. Yeah, it depends on the character set that you're working with. Now, over here, I was doing everything as a byte array, so I wasn't using characters. I was using byte arrays, and I know my file holds ASCII text, so I'm safe.
So Java strings are represented in UTF-16,
Yep.
which are 2 bytes. It might be the
I know.
fact that they're twice as large.
Right. That might be slowing me down because I'm using char at, and it's actually, when I build this string here, see, when I build this string to pass it to the, see, I build the string out of a byte array. That string might be twice as long as the byte array because it might be taking my ASCII chars and turning them into Unicode characters, which are 2 bytes each. So see, every time you step up to a higher level structure, you start losing a sense of what you're really doing. Now,
I think that Java strings are still represented by an array, so char at should be just as
yeah.
fast
Now,
as an array access. It should just be an array access.
yeah, you know what I
Like,
maybe should do here is not pass strings, but pass arrays of chars. Because that's what I'm using. Remember over here, everything is an array of char. So why don't I just pass to my worker, instead of passing to my worker a string, I could pass to my worker an array of char. Okay, so that's it. So now I'm going to sit there and go, why did this thing slow down so much? I gave it 12 cores and it's 5 times slower than the serial version. So I start looking for high level things that are actually possibly hurting me. Okay, so I could maybe, like, I can get rid of that string by actually passing to my task an array of char. So I'd have to pull out of this big buffer, but that should be really fast. Building a smaller array out of my buffer should be way faster than building a string. And then down here, I can step through an array of char. So I can try, that'll be an experiment to try. Okay, so this guy builds lines, okay, by finding new line characters and then building a line and then passing it to the worker thread, okay, and then then the worker thread has to step through the string. Now, this is way faster than the other parallel version. Remember the first parallel version, which was using nothing but high level code, using scanners and everything. This took, even though this was in parallel, it was as slow as, it was incredibly slow. This one is way faster than this one, but this one is still way slower than the serial version. We should be able to speed up the serial version. Okay, so let's actually start playing around with this. Let's first of all get rid of the file input stream. Okay, let's get rid of the file input stream and actually have it work with system.in, just like this guy did. Just like this guy, he read directly from system.in.
Yeah, I wouldn't expect that
I wouldn't
system
expect,
pipes be able to handle that much data that fast.
Pardon me?
I wouldn't expect system pipes to be able to handle that much data that fast.
Well, this one did.
It did. You're
This
right.
was the super fast one. Okay. All right. So now I'm not going to use a file. So now I'm going to use IO redirection to redirect the big data file to this guy, and he's going to be read from system.in. Okay. So, oh, and then I don't close. I can get rid of the line of code that was closing the file input stream. Doesn't need to be there. Okay. Now feed it the data file as standard in. Does it look like it's beating the other one? They're time. You can look at the time. Like at this point, he's taken about. Oh, it did help. It did help a lot. I'm a little bit surprised by that. File input streams are not very good. Okay, so we got a pretty good performance gain by avoiding a file input stream and going to system.in and IO redirection. Who would have guessed that? Okay. In the real world of trying to write fast database servers, and this is what Google pays people big sums of money for, is to just try to sit there and hammer away at code, trying to figure out, what if we change this one line? Can we get 10 or 15% performance gain? And knowing what's going to be fast and knowing what's going to be slow. We actually got a pretty good performance boost, though I don't know why the output ended up, the output ended up being kind of unsynchronized. Oh, that's because the worker threads were not, the output's coming from the worker threads. And oh, when this guy was done reading this guy finished the IO, and oh, what I need to do is not print the elapsed time until I know that the worker threads are all done. I would need something in here to somehow know when the worker threads are all done before I print out the elapsed time. So what we saw here was, at this point, all the IO had been done, but there was still some computations left to do. So the IO, the system.in whipped through that IO super fast, which is what we want. See, we actually got what we wanted now. We actually now can see that we got a performance increase by doing the IO in one thread, and it managed to get through the IO very fast. And then there was the matter of waiting for the thread pool to get done with the computations. Okay. All right. So we got a pretty good performance boost. Okay. Nope. Oh, okay. All right. Now let's see if we can get another performance boost. Okay. Now we said another performance boost might come from not building a string, but building an array and passing an array to the workers. Okay, this is going to take a little bit more work. The worker is going to take an array of bytes. See, our fundamental data structure that seems to be fast is an array of bytes. So replace string with array of bytes. Okay, so one line is now going to be an array of bytes. Okay, and then over here, I can change this to these to array axes. Okay, now I can change these to array axis. Okay, do I have to do, oh, and then length will be a field, not a method. Okay, I think that's all I need to change in this guy. The task will take in, oh, and yeah. Oh, I have to change this guy to byte array. Okay. If anybody sees anything missing, pardon me?
Got an extra Y in byte.
Where? Oh, yeah. Which?
There you go.
There. Okay. All right. So I think this guy's set up now. So he's going to take, instead of a string, he's going to take an array of bytes. Now the little bit harder part is to replace this line with a line that builds the array of bytes. Okay. So okay, byte one line is going to be a new byte array of size what? It's size oh, this is the size. That was the length of that array. That, yeah. Okay, there's the size. Okay, and then I need to, I probably just write a little for loop to copy from the this byte array into this byte array. There, let's see, and I will just say one line I equal C. Now I gotta be careful. What am I getting? I'm copying.
I believe you also stopped making a one line and started typing online.
Oh, yeah.
You did it in line 44. Yeah.
Yeah, that's okay. One line. Okay. Now let's see. I'm copying. So this will be offset plus I, right? Offset is the beginning of the line. It's offsets where the last offset is where the last line ending was, and I is where I currently am. Oh no, I have to use a different letter here. I've already used I. You know, this better be J. Okay, and okay, I think that's right. So online one line J is the original the big byte or the big buffer, offset where I am at the beginning of the line, and this is how far into the line I am. Okay, so that, let's see, does it compile? Nope. Let's see.
Line 49 has a capital L in one line. I don't know if that's it.
Oh yeah, that's kind of stupid. Yeah. Well, okay. Yeah. Let's see. Let's be. Yeah. How did I have it before?
Oh, it looks like it was capitalized before.
One. Okay. One line. Okay. One line capital. Oh yeah, it was. Yeah. So it was one line capitalized. So let's be consistent. Yeah. One line capitalized. Okay. All right. So now we've gotten rid of the string factor. We're just working with byte arrays. Okay. Each byte array is one line. Okay. Oh, notice that this file actually has one advantage over this one, is that now I don't have to worry about aardvark straddling a buffer, or do I? Maybe I still do have to worry about that. Yeah, I still do have to worry about that. Yeah, if aardvark straddles one of these buffers, I'm still going to miss it. So if no, I'm sorry. Yeah, here's where I read the buffer. Yeah, if aardvark straddles that buffer read, if an aardvark straddles that buffer read, I still will miss it. Okay, so I still have the same problem. Okay, compile, run this. And there's a bug because I'm not finding any aardvarks now. There's, yeah. Okay, so it was fast, but
Oh, you left I's in the 4 line, line 45.
okay. Oh, good. Yeah, that should be a J there.
There's 2 of them in the middle too.
Oh, yeah, this is a J. See, copy paste all, companies can lose billions of dollars on mistakes like those. Okay. All right. So, okay. Okay, now. Yeah, something's still wrong.
Yeah.
No,
Oh,
this one is supposed to be I.
Yeah.
That one is supposed to be I.
It is? Oh,
Yeah.
okay. Yeah, you're right.
Yeah, that
I
one
see
should
mine now.
still say I. Yeah, that's the length of the array. So this one is I minus offset, but this one was supposed to be J, and this one's supposed to be J, and these are J's. Okay.
Okay.
Writing code is fun. See, this
Yeah.
is what this is what you should never do is code in public. That's what you you guys are going to be doing it pretty soon. You'll get job interviews. It's the one time in your life when you have to code in public. Yeah, but you prefer not to have to be doing it this way. Okay.
Right.
And there's still a bug. We didn't change that many lines of code.
No.
Hmm. Notice how the trouble was that trying to write lower level code is tricky. Now we're finding we're gonna notice that this thing just kind of got lost at this point. It's not working very hard, but it's still running. It doesn't seem to be doing much. Okay, I'm just gonna kill it. Okay.
Is it the offset?
Offsets where a slash n was the last slash n was found. See, offset is where you found the last slash n. Well, one past it. So it's the character right. Offset points to the character right after a new line. The main thing we did was instead of building a string, we're building our own array. So instead, this built a string out of this buffer, starting at offset and that length. Okay, so that was from this buffer, starting there, that many bytes. So we should be doing the same thing here. We should be starting, we're using the buffer C. We're getting things out of the buffer C. We're starting at offset, and we're incrementing through C away from offset by that many bytes. And we're putting things in one line. Okay. And then we pass a reference to one line to the task. The task builds an object with a reference to one line and which line number it's what line number we're at. And then did we do anything wrong here? We start at the beginning of the line and we oh darn it. I don't see a mistake. We didn't make a big change. What would be something we could do to debug this?
Oh, print some of it out. I don't know. What's that noise?
Let's do something dumb. Let's print these things. Let's see. How do you print an array? You need to use.
You could do the arrays two-string.
Is that how do you call that? I forgot.
I think
Arrays.
it's arrays dot two-string and then put the name inside the parentheses. I think.
Do I have to import anything to use this?
Yeah. Unless you already have util already imported.
No, I probably don't. Okay,
Okay.
so system.out.println arrays 2-string 1 line. Okay, and then
Yeah, I believe it's util arrays, I think.
java.util.arrays
I think so.
or just
Yeah,
arrays.
just that. Yeah.
Yep. Okay. Now this is going to print out a lot of stuff, but yeah, it might give us a sense of if there's something really bad happening here. So pass it the data array, stop it. Couple empty strings. Notice that they're printing as ints, not characters.
Yeah. Huh. Maybe that's why it's not finding aardvark.
Pardon me?
Maybe that's why.
Well, no, because well, comparisons should be okay. You know,
Or do you have to cast those to?
I don't think so. I'm pretty sure that. Well, remember they worked fine over here. See, it's the
Oh, yeah.
exact same thing we did over here. Same data types and everything. So yeah, characters can substitute as ints.
Right.
Okay, or in this case as bytes. Yeah, a character is a byte. See, this looks, it doesn't look weird. Lots of blank lines, but we know that, if you go back, if you open the original file, it had a lot of blank lines in it. Now, I'm gonna kill this. Now there isn't, if I just want to see what I'm printing, I could do another thing here. I could where is it? Oh. Instead of 2-stringing the array, let's build a string out of the array. I think you can say new string. I think there's a string constructor that takes the array of bytes. I think there's a string constructor that'll take an array of bytes and turn it into a string. Let's see. Oh, that's weird. We're getting no output now.
Need to go. Does it need to go inside that for loop? Or?
No, I want to print the, when this method is run, I just want to print out the array that this for loop is walking through. It worked. Let's see. It was printing out a minute ago. Oh, I know. I forgot to redirect standard input to it. Stupid. I was calling it wrong. Okay. I forgot to redirect standard input into, this is the version that needs standard input redirected into it. So, okay. Okay, it needs standard in redirected into it. See, there's my data file. Okay. It looks like I'm stepping through the data file pretty well.
Yeah.
Okay. But you notice that the output's coming in bursts. Something's kind of, see,
Right.
we're getting bursts of output. You know, why are we only getting bursts of output? Why aren't we getting a steady stream of output? What went wrong? And you know, we're using all our cores. The thread pool is very busy. We're still in the Bible, which means we haven't gotten very far through the file. But at least we see that we've built the arrays correctly.
Right.
The arrays got passed down to here reasonably well. Now, let's see. We got rid of the file input stream and used system.in, and that helped some. Okay.
Right.
So we were a little bit surprised. Yeah, that's a little bit surprised. Now we're trying to get rid of the strings and replace them with byte arrays, but something's gone wrong at this point. And actually, those were the only two optimizations I even could think that could possibly speed this guy up. So I don't think, you know, I was hoping that this would really speed it up, because this is, I can't think of any other optimization that could, you know, what stands between this one and this one? This is the super fast serial one. You know, what stands between them? Well, this one's using system.in, which seems to be a little bit faster. And this one's doing everything with byte arrays. You know, it's just doing everything with low-level byte arrays. And at this point now, this one is doing pretty much everything with low-level byte arrays. It has to copy each line, which is actually kind of bad. You know, and you know, we actually, you know, we do have to be. There is reason to be concerned about the fact that we're copying data here. What if the copying takes as long as the processing of the data? Yeah, if the copying takes as long as the processing, then this could cause us grief, because it's just more work. Yeah. Over here, oh, you know, where is the potential for speed up over here? And let's go back and think about, this is the serial one. Okay, where is the potential for, actually, see, leave it up to you guys. Why would you expect this one to be able to become faster? Now, I know that there is a potential for speed up in here, but where is it? This is really fast. You know, where's the potential for speed up? Think what the code does. The while loop does what? This guy does what? What's the job of line 20?
To read from the buffer.
No, to read into the buffer.
Oh, read into the buffer.
Yeah, read from the input stream to the buffer.
Okay, I see.
Okay. Okay, and then process what you just read. Read another buffer, process the buffer. Where's the potential for speed up?
To start reading in a buffer while you're processing another one?
Yeah, you right now there's no, while I'm blocked in while this thing takes a while to get data from the stream, I'm not doing anything. See, what I really want to do is interleave this processing of data with this reading of data. There's the potential for speed up. There's actually the only potential for speed up. The only way this guy can be made faster, he's already super fast in this loop. The only potential here for speed up is that when you've read, while you're reading a line, you should be processing the previous line. While you're reading the next line of data, now here what we do is we read one line of data, then we process that whole line of data, then we read another line of data, then we process that line of data. What we want to do is read a line of data, and then simultaneously start processing the line we just read while we start reading the next line in parallel. The goal really is to do in parallel, read the next line while you're processing the previous line. Okay, that's exactly what this guy is attempting to do. He's attempting to do something like that by having this loop up here. This loop here reads a line, but doesn't process the line. Well, it does a little bit of processing. It needs to build the buffer to send to the work queue. But the goal would be to very quickly pass off that line to a worker so we can go read the next line. And then the workers can be working on lines while we're blocked, while this thread is blocked waiting for a line to be read. The workers could be reading, they could be processing data. So that's why I said that we need to do this thing of breaking apart the reading step from the processing step and have the processing step done in a pool. But there's a problem. We have to build the processing step before we can put it in the pool. And right now there's a bug in this. But then there's still the question of whether even this copy step here might actually kill us. It might be a little bit too much work here. I have a feeling it's not going to. I don't think this copying step is going to be a problem. Okay, I have a feeling it's not going to be a problem, but it might be. Okay, but see, that's where the potential for speed up is over here. This loop here is very tight, fast loop. We're not going to speed it up, but we do have block. While you're blocked, you're not doing anything. Process one line. Block. While you're blocked, you're not doing anything. Process one line. So we need, now. So this now has the potential, since it's got that fast loop here with just array access. But there's a bug somewhere. I really wish I could see it. I wish I could find where the bug was. Okay. If we find the, we'll quit now. If we find the, I'm going to put this code up on the website this evening, and you can look at it. And if you've got Andrew's data, if you've downloaded Andrew's data, when you download my code, there's the batch file that combine. Now I took the 1,000 largest files from Andrew's data, so I took the 1,000 largest files and put them in a separate folder, then ran this batch script on them. This little batch script concatenates all the files in a folder into one file. So it just concatenates them together. Okay, so if you download Andrew's data and you peel off the 1,000 largest files from it, then you run, or you can, if you want, you can do this on all of Andrew's data, but then you'll create like a 40 gigabyte file. So the 1,000 largest files created a little over 2 gigabyte file. Okay, so that built and this one, it actually is working out real nice. This 2 gigabyte file is about the right size for running experiments. Not too big, not too small. It turned out just by luck that by peeling off the 1,000 largest files, I ended up with something that was very good size. An experiment takes about 15, 20 seconds to run. And it turns out to be a very good size for getting the code working. And then after this code works, then we can go back to all the data, with, oh, actually, this is 1,000 separate files, and then we would, but this 1,000 separate files is equivalent to this one big file, but the code won't be. You know, processing one big file and processing 1,000 small files, even though they're the same size, is not going to be the same code. So we'll want to switch from processing one big file to processing 1,000 files. Then we'll go to the whole data set and try to process the 40,000 files. Okay, so that's kind of the logic of this. Okay, you can't bite off a huge problem at once. Yeah, notice that I'm really breaking things down into little bits and little bits. I'm constantly breaking things down into little, just like here, read the bytes in the file, then read the lines in the file, then search for the word aardvark in the file. But by biting things off little bit by little bit, I have a sense of when things are working and when things are blowing up. If I bite off too big a chunk, it's hard to know what went wrong. Okay, when you're writing performance code, you can't optimize 10 things at once. You can only optimize one thing at a time. So you've really got to, if you're really writing, you're really trying to do parallelization right, you have to ease into it real carefully, just trying to optimize one small step at a time. Just because you got all 12 cores running doesn't mean you're doing anything useful. We've seen that already. We've seen how to slow programs down with 12 cores. Okay, it's a fun thing to do. It's satisfying to see all your cores running on a thread pool, but we've seen how you could very easily use all your cores to slow things down. So what's hard is to use all your cores to speed things up. And we're seeing how that's not easy to do. Our fastest program is still the serial one. That's kind of discouraging. And when I read the stuff in the literature, that's not unusual. It's when you get past textbook examples and you get to where you really want to do something in the real world, sometimes trying to beat serial code is not all that easy. Just, it's easy to get 12 cores running. It's hard to get 12 cores actually speeding things up, unless you're doing something that's trivially parallelizable. And what becomes hard is what we're trying to do here: mix I/O with work. Usually when things are trivially parallelizable, there's only work, only calculations, no I/O. What we're doing here is the hard thing. This is the really hard thing, to interleave I/O with computation and try to get it to speed up. So we're trying to do something that's a tricky thing to do, and we're seeing that the thing to beat is the really super fast, low-level serial program. That's still the thing to beat. Yeah, and it beat TextPad by a mile. It ran in 5 seconds. It beat TextPad by a lot. It's beating all our parallel codes so far. But I'm curious to see what happens to this one when we fix when the bug gets, when this one doesn't have that bug in it. Maybe it'll do the fast thing. I don't know. Okay, so I'm gonna put this code up. You can run it. I'll put all these versions up there, and get Andrew's. Oh, wait a minute! I didn't put the link to Andrew's code, did I? Data, did I?
I don't think so.
Oh, shoot! You guys, yeah, I forgot to give you a link to Andrew's data. Somebody send me an email, because I'll forget again today. There's been so much work to do. I mean, I'm sorry. I'm behind on emails. Some of you may have noticed you sent me emails and you haven't gotten answers from them yet. I've got a lot of students and a lot of classes. So I forgot to give you the link to Andrew's data, because the data is really nice. I mean, it lets us do these really cool experiments. The data is really good to have. It's not so easy to get this kind of data. So I'll try to remember to I'll put a link up here to Andrew's data, and then I'll put the code in in a zip file, and download and play around with it. Hopefully the code will compile, and if I find the bug in this one that's potentially the fast one, I'll let you know that I found that bug. But play around with the code. Look at the different versions and play around with them. Okay, and if you have questions, send me emails. I will get to them. I've been, it takes me a while. Answer these emails is not easy, and I've been getting a lot, a bunch of classes. So, but send me emails if you have questions, and I'll try to answer them. And I hope I got to remember to put Andrew's data up, a link to Andrew's data up there, so that you can download it, because it's a very good. You may have to clean it up though. The data does to make some of this stuff work. You do need to clean the data up. So you can try. That's another little good project. Is I used that DOS to Unix to clean it up. And Andrew, what did you use? You used what was
Actually, for me, that data set is more or less already cleaned if you're on Linux. If you're on Windows,
yeah,
good luck.
Yeah. But this DOS to Unix did a good job of cleaning it up. It converted everything to Unix line feeds, and it told me when a file had bad data in it. So I just deleted the files that had bad data. There was about 25 out of the 1,000. I think there was about 20 of them that had binary data in them. So I deleted the 20 files that were bad. So that wasn't a big deal.
For me, how I dealt with those was I was using grep. So I just told grep, treat everything as text, because more than likely it's text.
Yeah, and my preference was just to get rid of the files that had the bad data in them. Yeah, so my goal was to get rid of the files with the bad data. Okay, so I'll stop there. Okay, so I'm gonna end the meeting now. But again, please, if you have questions, send me emails, and I'll try to answer them as quickly as I can. So good night. Bye-bye.
Bye.